Good day, everybody. Before I show you this proof regarding town numbers, I want to go ahead and just do a concrete example. Now, this little d is intended to be the function that counts the number of divisors of the input argument. It's normally associated with a positive integer. Okay, sometimes I use tau as, I guess, Greek for t, but I'm going to use little d to count the divisors. Now, so let's keep going here. Now, prime factorization, you can just enumerate them. You can list all the divisors of 225, including 1 and 225. Or you can, there's a function of the exponents that gets the job done also. Notice that this is 9 times 25, and you can write that as 3 squared times 5 squared. And I've said this a million times, but because you can allow for 0 to be the exponent, this actually gives you 2 plus 1 times 2 plus 1 divisors. And I won't go through the proof of that, but it's pretty easy to see that if one of the exponents is 0, 1 or more, that gives rise to divisors as well, because anything raised to the 0 power is just 1. Okay, but we get 9 here. Okay, we get 9. And again, if you were to list all of the divisors of 225, 1, the next one would be 5, the next one would be 15, and so on. If you were to list them and count them, you would get this number 9. Now notice that d of 225 divides 225. Okay, since 9 times 25 is 225. Okay, so d of 225 divides 225, and that's literally how that makes 225 a tau number. Okay, 225 that makes it a tau number. Okay, I'll just put tau underneath it. Okay. Now another way to represent, like right here, your m would be 9 in this case. So another way to write this notation, d of n divides n, it's equivalent to saying n is equal to d of n times some integer m. In this case, our integer would be m. Or no, excuse me, integer would be 25 and d of n would be 9. Sorry about that. Okay. So we want to prove that if n is an odd tau number, we want to prove that 2n is a tau number. And you can check that with 450 if you want. Okay, but 450 would be 2 times 225, and that's also a tau number, which it's a very simple computation. You get 18 divisors for 450, and 18 does divide 450. Okay, but anyway, let's just prove the general case here that if n is an odd tau number, odd's important, prove that 2n is a tau number. Okay, now so 2, that's where the n is specified to be odd. Okay, n is specified to be odd just in the problem statement. And so that makes this divisor function to be what they call multiplicative. Okay, now 2 is a prime number, and any prime number has 2 divisors. So notice how d at 2 of n, d at 2 times n is just 2 times dn. Okay, now here you get just by solving this in this fashion, you solve for d of n and you get n over m, where m is just the integer, the other factor. You know, d of n is actually a factor of n if n is a tau number, right? So you see how we get this, and it's a fairly straightforward proof. So we get this statement right here. Okay, everything so far so good. D at 2n just by multiplying through by m up here, right? Okay, and so you see the m's would cancel. If you multiply through by m, the n's would cancel, and you have 2n. Okay, but this that means we've proved what we set out to prove. Okay, we proved that d at 2n is a factor of 2n. Okay, d at 2n is a factor of 2n. That's what this says. Okay, so it's QED time. It's a very simple proof, really. So QED on that. And again, the only thing substantive, I guess, about this really is just knowing that if 2 numbers are co-prime, then you can split them apart. That means the function is a number theoretic multiplicative function. Okay, and so that completes the proof. You know, we've shown that d of 2n is a factor of 2n, which just think of n as being equal to 2n right here, okay? And you'll see why this proves what we set out to prove. Now, let's come up here and just check 450, okay? Because 2 times 20, 450 is equal to 2 times 25, right? 2 times 225, what did I say? 2 times 225? Okay, and we need to show it's a Tau number, but D at 450 is 18 because you have a 2 in there that would, it stands to reason that would make that. Remember, it was 9 a while ago. Now it's going to be 18. But D at 450 is actually 18. You can verify just using the same process I did. Just if you tack on a 2 right here, you would have the exponents would be 2 times 3 times 3, which is 18, okay, when you increment them. So that does divide 450. Okay, 18 times 25 is 450, okay? So you see, again, this right here proves it in general. This is just one special case, okay? So that is all fairly easy proof. And then the Tau numbers are actually fairly interesting. There's some other results that aren't quite as trivial as this that are pretty interesting in Zielinski's paper. If you guys want to take a look at Joshua Zielinski's paper, I think he penned that document back in 2002. I'll try to remember to put something about him in the description so if you guys care to read more about that. Okay, thanks for viewing.